All right, so this last set of solutions that I'm putting together for today is going to be over this circuit analysis number 2. Circuit analysis number 1 I did in class, so you can look at your notes from class to see those solutions. So this one starts with this circuit that we have here. And we'll just solve this right here on top of this so we can draw on the picture so we don't have to draw it again. So whenever you're looking at a problem like this, it's helpful to kind of take it in and try to understand what the circuit looks like before you start writing on it. So I would look at this and say, well, where should I draw my currents and where is the current not going to be present, is going to be non-zero? And then in thinking about that and drawing your loops, you'll end up seeing like the easier ways that you might be able to solve this. So I'm going to draw this current. I'm going to call this one I1. This is going to be an I2. This is going to be an I3. And this I2 is actually the same current I2 here because this capacitor is fully charged in the steady state, which means that there's not going to be any current flowing across it. So now, when I'm going around this these loops here, what I'm going to do is I'm going to draw, this is going to be some loop 1. Here is some junction. Here is some loop 2. And here is a loop 3. Okay, so when I did this, I saw that I have 4 things that I don't know. I don't know current I1, current I2, current I3, or charge Q that's on the capacitor. So because I have 4 unknowns, that means I need 4 equations. So the first equation that I can write is the junction equation. This says that I1 is going to be equal to I2 plus I3. The second equation that I can write, we can write loop 1. So loop 1, going around this loop, we end up seeing that this is going to be minus phi plus I1 R1 plus I3 R2 for the way that I have this written is equal to 0. 2, this is going around this loop. We have this is going to be I2 R3 plus I2 R3. Those are the same resistor. Minus I3 R2. Because the current is going down, the loop is going to go around in this direction. It's opposite direction, so that's a negative sign. The last loop that we have is this one right here, where we're saying that we're going around the loop in this direction. So we're going the clockwise direction. That gives me a plus Q divided by C, and then a minus I2 R3 is equal to 0. Okay, so now if we wanted to solve this, what we could do is per this condition that we have here, it says that imagine the resistor R1 is equal to 0. So that means that in this equation right here, this is let's write this in red. This is 0, and then that's actually the only loop that I have, that one. So here then, what that means is that we can solve for I3. So I3 from this, and again, make sure that you're working out these all the steps yourself. This says that I3 is going to be equal to V divided by R2. And we can take that and we can evaluate this equation here then. So I2 is going to be equal to I3 R2 divided by 2 R3. So we can take this and we can plug that in there. And then once we have that I2 in the last equation, we can say that Q is going to be equal to C I2 R3. Okay, and then that's the whole thing. So for a problem like this, if this was 25 points, I'd say probably 20 of the 25 would be just setting up the equations, and then that works out sort of nicely because we have 4 equations. That's 5 points apiece, and then 5 points for doing the algebra for the rest of it. So the majority of the problem is not in the algebra, but you need to make sure that all of the signs that you have for these terms are consistent with the way that you drew your loops. And that's why it's very important to draw these, because I'm not going to give a lot of partial credit if you have incorrect signs and there's nothing here indicating what directions you're defining. It makes it really kind of hard to grade. And it's not a difficult thing for you guys to do to draw on those. So the next problem, this is going to be another problem that's really similar to this. So we want to draw our currents. So here's some current I. This is the same current I. There is no current over here in the steady state because the capacitor is fully charged. So we can draw our loops going around like this. This is some loop 1. This is some loop 2. So for loop 1, this is going to be minus V plus I R1 is equal to 0. V is going to be equal to I times R1. So I is going to be equal to V divided by R1. For 2, we have our charge that we put on a capacitor here. So that's going to be a plus Q and a minus Q. This is going to give us a plus Q divided by C minus I divided by R3 is equal to 0. So we're solving for Q from this one. So Q is going to be equal to Q is going to be equal to this is wrong. This is not I divided by R3. It's I times R3. So this is I times R3. So Q is going to be equal to I R3 times C. And so then we can take this and we could plug it in here if we wanted to. So we'd say that this is going to be V R3 over R1 times C. Now, here, this last part of the question says, if the electric field that can exist between the plates of the capacitor is E max without the capacitor burning up, what is the biggest battery that you could put in the circuit? And so this is going to be relating the electric field to the difference in electric potential. So this is V is going to be equal to negative integral of E dot dl from R vector 1 to R vector 2. And so here, this electric field is a constant. You're going to be integrating from 0 to L or D, what the distance is between them. So V is going to be equal to E max times D, which is the same thing as Q. This is going to be Q divided by C. And so we're given what this C is, and we found what the charge is on it. And so from that, we can solve for what E max is. I'm going to skip problem 3. This is kind of a challenge problem, and I even wrote here that this was an especially hard problem for the exam this year. I wouldn't ask you one quite this complicated, but it's an interesting problem for you to think about and to work on. I think those of you that decide to work on it are going to find that it's a fun problem for those that enjoy these kinds of things. So problem 4, it's basically just 3 quick circuits that we're going to have here. So this is going to be some current I. We can go around our loop. This is going to be minus V plus I R1 minus V plus I R1 plus I R2 is equal to 0. So I is going to be equal to 2V divided by 2R1 plus R2. Here we have, again, something similar. We have 2 loops in this case. So there's 1. Here's a loop 2. We draw a junction. So this is going to be I1. This is going to be I2. This is going to be I3. I3 is going to be equal to I1 plus I2. From loop 1, we have minus V plus I1 R1. Then we're coming around this loop, and this is going in the opposite direction. So this is going to be minus I2 times R1 plus V. It's the same voltage, so this is rather interesting. So then we have for loop 2, so these are actually going to cancel each other. So this might actually be a situation where nothing happens, but you can see that algebraically once you go through the whole thing. So for loop 2, this is going to be minus V plus I2 times R1 plus I3 R3 is equal to 0. So what we end up having here then from this problem is that we have I3 is going to be equal to I2 plus I1. We have I1 R1 is equal to I2 R1, and V is going to be equal to I2 R1 plus I3 R3. So these are the same resistance. So I1 is equal to I2. That says that I3 is going to be equal to 2 times I, if I redefine that there. And then say that this is going to be I. So this is going to be V is going to be equal to V is going to be equal to R1 times I plus R3, which is going to be 2I R3. And so at the end of the day, what this ends up saying is that I is going to be equal to V divided by R1 plus 2R3. And then because we have this I, we can use this and find what I3 is. It's just double that. Okay, so this one right here, similar situation, go around the loop. Here's loop 1. Here's loop 2. So for loop 1, we're going to have some current, and it's actually only one current in this circuit because of the capacitor that we have here. So I'm just going to draw that as that current. So that we're going to have a minus V. We're going to get a plus I R1, plus I R1 minus V, plus V, that one's a plus V, is equal to 0. So that's, these are going to cancel. Actually, this says that the current is going to be equal to 0. So that's kind of interesting because then when we go around this second loop, loop 2, all we have is that minus V plus Q divided by C, if I'm defining this to be plus and this is going to be minus, is equal to 0. And so all this one has is just going to be that this charge Q is going to be equal to V times C. And that's it for that one. All right. So make sure that you're practicing these. Like I said, I go through these very, very quickly because I've done them a lot. But it takes time and practice to be able to, even to really understand exactly what it is that I'm doing. It's not enough to just look at symbolically what I'm doing. You really need to understand how all the pieces are connected. Okay, so best of luck studying over the weekend. I will be available in Slack if you have questions as you're working on things. Definitely post them. Show me the work that you have. So if you have a question that you have on a particular problem, say this is the problem that I've done and this is how far I got and this is a part that's not making sense to me, and then I can reply to you and then talk to you about what it is that you've done. Okay, so that's going to be it. Have a good weekend.